Okay, we're ready to talk about routing for a few minutes, and we bring over the objectives one more time. We'll look at all of them, and then I'll try to tell you which ones we're going to cover in each element. The actual minutes of lecture that we're going to do, really not that much, but we will cover the objectives. 25% of the test is on routing fundamentals, and fundamentals, I think, is the key. The ICND2 is where the configuration becomes the larger part of the course. You'll find that ICND1 is the prerequisite for a number of different certifications, including CCNA. ICND2 is where you actually get the CCNA, where we do more configurations than an ICND1. So routing fundamentals describe the routing concepts, packet handling along the path through a network, forwarding decision based on route lookup, and then frame rewrite. And then we'll talk about the components of the routing table: prefix, network mask, next hop, routing protocol code, administrative distance, metric, and then gateway of last resort. And then 3.3 describe how a routing table is populated. 3.4 configure, troubleshoot, and verify. Inter VLAN routing is a thing called a router on a stick, which we will configure. Compress static and dynamic, compare and contrast static and dynamic routings. We'll look at that. And then configure IPv4 static routing, a default route, network route, host route, floating static routes, different ways to do those things. Troubleshoot, configure, verify, troubleshoot RIP-v2 for IPv4. That's the only routing protocol that we'll be doing, and you notice that the next objective here in the 4 series is infrastructure services. To go back and how much of each is in these things, 26% is switches, LAN switching, and then back up here, 20% is in network fundamentals. So with that, kind of a look back at the objectives, the routing concepts, packet handling, forwarding decisions, and frame rewrites. The things that were in the objectives. So when we go here, the routing decisions, the primary function of the router is to determine the best path using the route table. And okay, so what does this mean? The best path based upon metrics that we'll use, and we'll talk about metrics a little bit later. And directly connected, it may have directly connected networks, and it's going to use the ARP table in order to know where to send those things. A little note here, the addresses remain for 4 hours, so the ARP cache is going to be a 4-hour arrangement. If not there, if the MAC, what was it? It's IP to MAC, right? If we don't have a MAC address for an IP address, then we go through the address resolution, the ARP ARP protocol. The remote network, if it's not connected, we're going to forward it to another router. And if no route is available, we use the default router, the gateway of last resort, as long as we have configured it. And what does all this mean? Remote route and all that other nonsense here. ARP table, determine the best path using the routing protocols. If we have a number of different things, and I'm going to just attach random addresses. 192.168.1.0 network is here. 192.168.2.0, 192.168.3.0 is here. The only thing that our router knows about serial connections, about when it first starts up, is things that are directly connected to it. So in order for us to have a routing topology using either static, and we'll talk about static and dynamic routing protocols, using one or the other, we have to tell the other routers about it, how to get from one location to the other. If we're using a dynamic routing protocol in some variant, what this router is going to do is tell this router, or if we have certain protocols, all the routers using a multicast, I know how to get to 192.168.1.0 network. If we're using something like RIP, it'll tell this router. What it will then do is increment the hop count by 1, yep, 1 router away, and it'll tell the next guy that I know how to get to 192.168.1.0, and so it's going to have the addressing, the next hop address going this direction, but going this way, the next hop address is going to be the IP address of the next router. The next hop address needs to be the directly connected one, simplistically put. There are other ways that we can do that, but basically is we're going to tell it to go to the next router. So we have the primary functions determine the best path, and the best path generally going to be using a dynamic routing protocol, because what we don't want to have to do is update it every time there's a little change. The dynamic routing protocols will do that for us. If we use a default route. If we use static routing and any change, we have to go in and configure it, and we will talk about those a little more. But the packet forwarding decision tree here, a packet arrives at the interface. The router searches the routing table for a match. Does the destination IP address match the subnet of a directly connected interface? If that's yes, checks the ARP cache to see if it's available, and if it is in the ARP cache, then it knows to send it. Otherwise, it's going to go through the ARP process. If it's not directly connected, we have a no here. Is it on a remote network? Yes. Encapsulates the frame and forwards it out the interface of the next hop. When we say encapsulate, we're really talking about layer 2 encapsulation, and we're going to look at that here a couple of slides. Why would we have to do that? Because, and we'll look at it, we'll talk about it. Yeah, you know, you may have figured me out by now, but if we're going to send it to layer 2 along the path, we're going to send it to the destination IP. We'll say 192.168.1.3 is the destination IP. It's not going to change, but when we get back here, the source MAC address will be the computer, and the destination MAC address is going to be the interface of the router. As it leaves the router, the source MAC address is going to be the outgoing interface. The destination MAC address is going to be the MAC address of the next hop router. When we get here, the source MAC address, and the computer down here, the destination MAC address. The IP address never changes, and when we get a little farther, one of the objectives was frame rewrite, and that's exactly what this is frame rewrite. So it encapsulates the frame and forwards it out the exit interface to the next hop. If it's a remote network, no. Is there a gateway of last resort available? No. It drops the packet. If it's yes, it encapsulates it and sends it there. The remote network here is in the routing table. Is the remote network in the route table so that the router knows where to send it to get to its destination, one hop at a time. Packet handling. Routing is moving information across an inter-network from source to destination network. Forwarding is switching, and these are kind of like, okay, so which is which? What we want to be able to do is to use switching, because we switch in hardware, we route in software, and anything that we can do in hardware is typically going to be faster than anything we do in software. So routing is moving the information. Forwarding or switching is the router finds the outgoing interface, and then the packets are moved between the interface using switching, and it uses an adjacency table. An adjacency table is basically what would look very similar to the MAC address table in a switch. An encapsulation is attaching the control information in the form of headers. And the headers, we've looked at a number of them. We looked at the TCP header, the IP header, and the layer 2 header, the data link header, and we're going to look at it again here just in a second. So the process here is packet handling. routing, forwarding, encapsulation. What we're doing in the forwarding logic, when a receipt of a packet, the router uses the frame check, the FCS frame check sequence, to be sure that it has not been modified. Once that happens, it discards the old data link header, the destination and the source MAC address, and the ether type, just like we talked about before. Everything else, including the IP address here, is going to be in the data, the CRC and the FCS. So it discards the old data link header, compares the IP destination address to the routing table, finds a match where it's going to go out, and then it encapsulates it in the new header and trailer and forwards it. So we put a new MAC address on it so that once we have determined where it's going, and if we have multiple, and we could have obviously multiple routers, which interface is it going out of, we have to find the MAC address of the next hop, and that's what the adjacency table helps us for. Helps us to do. The addresses are going to be in this thing called the FIB, the forward information base. Let me see if I can drag something over here while we're got this and kind of talk about this a little bit using, I guess, an image here. If we look at one of these guys, this one's probably going to have the best route table. So let's go into it. I can't remember the password. Show IP route. When we go in here, we talked about directly connected. That's what it knows about. So the 10.10 network is directly connected. The 172.16.10 network is directly connected. And here is it's an IP address, which is on that. It's going to be the IP address of the NIC. And then O is going to be OSPF, and up here you can see the abbreviations, what they stand for. C is connected, S static, I IGRP, R RIP, mobile, BGP, D is EIGRP, EX is external, and then OSPF, inter-area OSPF is the IA. So OSPF is a dynamic routing protocol. So to get to 192.168.10 network, it goes via interface 172.16.10.2, and it also goes out serial 00. We have both. We can, when we specify a static route, we can either tell it what the next hop address is, or we can tell it the interface to go out of. If it's going to the 192.168.20 network, it's going to go out serial 11, and then for the 30 network, it's going to go out fast Ethernet 00. Let me close this and we look at this thing. 192.168.10 network, 10.1, and then this was 10.2, which was the next hop address that was in the route table. 10.6 was the next hop address, and then the to get to this one down here, it goes out the Ethernet port. So when we look at those things, then that's what a route table looks like. How does it get from point A to point B? When we're talking about the adjacency, the forwarding table and the route table, what's different in them? And what I've done this, obviously you can see here, but if I show, let's show, we have this thing called CEF, Cisco Express Forwarding, and we'll look at a summary here. It's 21 routes, 0 re-resolves, unresolved, on 21 leaves, 15 nodes. If I just maybe simply show CEF, it tells me 10, 10, 10, 2, the next hop to get to each of these things, receive, and then 224, 0, 0, 0, it's going to drop, going to receive, and then we have a directly attached. It knows which ones are directly attached to it. So this is what the forwarding information base would look like, and it comes from the IP route table that we had looked at a little earlier. Probably a little confusing, sorry, but different things to get there to get it from point A to point B. Forwarding, if there's no match in the routing table, then we're going to use the default route, the gateway of last resort. And again, if there is no gateway of last resort and it doesn't match any of the networks that are available in the route table, then it's going to be dropped. Single entry match is forwarded to that interface. And then if we have more than one entry, we use the longest prefix. Let's fix that prefix. For example, packet destined for 192.168.32.1 arrives on an interface with the following routes. 32.0 with a 24-bit mask goes out of 10.112, and this could happen. And then for the 192.168.32 with the 19, it goes out the 10.1 or goes to the 10.1.1.3. So it's sent to 10.1.1.2, the gateway. That'd be the next hops in this case. I said out, but it would be 2 because it's the longest prefix, the one with the longest subnet mask, 24 bits versus the 19 bits. A detailed route example, I think we kind of have done this already. 192.168.1.30, we have an Ethernet IP packet, goes to the Ethernet interface 192.168.1.2, which is going to be the default gateway of this thing. And then subnet 192.168.4.0, out serial interface 00 with the next hop of 192.168.2.2 here, 2.2, and from that router 4 goes out serial 00, goes to 192.168.3.2. When it gets to 192.168.3.2, it's directly connected, so that's when it goes through the ARP process and finds the MAC address to send it to. And again, in the frame rewrite, we're changing the data link header, the MAC address, the source and destination at each location so that it can get from one device to another. We've looked at our route table a little bit already, and this is, in this one, the 10 is subnetted into one subnet. And this is gateway of last resort is not set, which means that we do not have a default route. No default route is available. So if its destination is not in this route table, either the 1610 network, 192.168.10 or the 192.168.20, then it's going to be dropped. So we have directly connected. The 10 directly connected is right here, and then the 172.16.10.0 and 10.4. The 10.0 network here, we have a 30-bit mask, is why we have these things, are directly connected. You have to have these addresses, these networks, in the route table, because that's what actually activates things in there. And then the 192.168.10 network via the 10.2, 192.168.10 network would be up here via the 10.2. The via is the next hop address, and then it goes out serial 00, which would be this one right here. So a route table, again, a look at what one looks like and what's in it. Frame rewrite, we have talked about. Many fields in the packet have to be rewritten when the packets are routed between the subnets. Both the source and the destination MAC address, the IP header checksum, time to live, the trailer checksum, and the CRC, because all these things are going to change. TTL, time to live, is how much longer does the packet have, and basically it's decremented by 1 every time it goes across a router. The incoming frame checksum is verified to confirm that no frame corruption or alteration has occurred, and then the incoming IP header checksum is verified to confirm that no corruption or alteration has occurred during transit. So checks it, rewrites the things that have to be rewritten, the TTL, the IP header checksum, CRC, source and destination, MAC address to get it from one device to the next device. So what we talked about was routing, and routing is getting it from point A to point B in the most efficient manner. We talked about the differences between a forwarding table, the forwarding information base, and the route table. The forward information base, think of it as a layer 2, and the routing table as a layer 3. The forward information base forwarding is going to be done in hardware, which is typically going to be much quicker than something that's done in software. And then we looked at the route table. I actually looked at the route table a couple of times, what it looks like, and part of what each of the components means. We'll talk about those a little bit more later. And then frame rewrite, the things that have to be changed as it goes from one device to the other. Source, destination, MAC address, CRC, the IP checksum, those things have to be rewritten before the frame can go out. Otherwise it's going to be seen as corrupted, or if you don't change the source and MAC, source and destination MAC is just not going to go anywhere. So with that, we'll stop with the overview and go on to, let's see what's next. Interpret the components of the routing table. So we'll look more specifically at routing table components in the next module.